This is a 3D printed RC bulldozer, built for the beach, the dirt, or anything in its path. The blade tilts and rolls for full control, while two high-power motors put power to the ground. And when the terrain fights back, drop the ripper and tear it open. Every part of this machine was printed right here at home, from the cab interior to the 95A TPU tracks. The result, a beach day game changer, a beam pushing monster, and a miniature tilling machine. But before you go and download the 3D files, I first need to show you how I went from idea to bringing you the most rugged dozer I could. Enter requirement number 1, which is that I want the tracks on this dozer to have enough power to push over a category 4 kaiju. And if I can't find that, well, then I want it to have enough power to at least pull me in a wagon. Which starts here with this N20 motor. This motor has been the beating heart of all my previous projects. They're cheap, readily available, and can be bought with a number of different gear ratios. The problem though is they're tiny. For instance, I used 3 of them in my RC Semi to get enough power to haul stuff around. I was able to get away with that because I was using these round things called wheels, which are pretty efficient, especially when compared to something like this track. Because of this, I've decided to upgrade from these little motors to maybe these bigger motors, or maybe even these much bigger motors if I can get away with it. For reference, the N20 has a motor diameter of 10 millimeters, while the others have respective diameters of 24 and 35. Which brings me to my next point. My main objective for the bigger motors isn't all just power. Yes, I'd like a little more, but ultimately I want longevity and reliability out of them. If you push this N20 motor at max load constantly by pushing stuff around like a dozer does, it's going to burn out pretty quick. There's just not that much area for it to dissipate heat. This larger motor is just, well, larger, making it a better heat sink. For something like this dozer, it'll probably never get more than a little warm to the touch, and that's the longevity aspect. Yet another point is that the gears inside the gearbox on the N20 motor are tiny, and sooner or later, one will strip out under the high stress of bulldozing. The gears on this bigger motor are massive in comparison and will be much harder to strip out. The bigger motor does come with downsides though, the primary one being they just take up more space. Therefore, I'll be building a larger model than what's typical, and what better models to use for inspiration than a Cat D11 and Komatsu D575A, both very, very large dozers. However, I will be capping the size so as to still be able to 1, haul it on the drop deck, and 2, easily fit it on a 3D printer build sheet. Others include having the following functions: blade lift, blade roll, blade tilt, ripper lift, ripper tilt, and lights, bringing our grand total of required motor outputs to 7, one of which I'm going to be switching to a servo for techie reasons I'll explain later. So 6 motor outputs or 3 dual channel H bridges will be required. Now I've got a rough idea on the electronics, therefore giving me an idea on how much space I'll need in the frame for said electronics. The first real progression step in any of these projects is creating the initial 2D sketch of the model. This is by far the most impactful step, as the angles and dimensions laid out here will stick around throughout the entire project, and making changes to those dimensions only gets harder and harder the further you get into the project. And this is what my final sketch ended up looking like, a blueprint for the rest of the build, if you will. Now I can take that one blueprint, duplicate it multiple times, and start extruding one piece of the dozer from each blueprint. Starting with the body, I extruded it 80 millimeters, which with a 3 millimeter wall on each side should give us 74 millimeters of internal space to use for the motors and electronics. I'm a big fan of the stanced out bulldog look on anything vehicle related. So I extruded the tracks out 40 millimeters, which should stick out from underneath the wheel arch just a little bit. Because the body is now taking shape, I can take my first stab at the blade, but almost immediately I scrapped it as it just looked super flat. My second attempt began by creating an overhead 2D sketch and giving it the proper side angles like the blade you see here. I then extruded it up and began the process of pinching and pulling at it until I was happy with the outcome. Fitting the blade up next to the dozer, I got my first glimpse at what this could end up looking like. As you can see, I've got some mock-up motors in this picture, and this blob right here is an outline of the same PCB I used in the RC Semi, as I would really like to reuse it in this project if possible. Transitioning into the track assembly, I started by splitting it into 4 parts: the track support, rollers, final drive, and of course, the track. I decided to secure the track support to the body using 3 attachment points, 2 below and 1 above, which should provide a super solid triangular connection. Now, a rule I try to follow when building these projects is to not print anything until 90% of the CAD is done, because it saves a ton of time when you start fitting parts together at the end. If it's rushed, you end up having to 3D print things 3, 4, 5 times when it could have just been once or twice. With that disclaimer out of the way and an emphasis on the I try, I started printing this track assembly out at about 20% model completion. But I think I have a good reason, which is that the tracks on this model will of course be subject to the most wear and tear out of anything else on here. So I want to work out the weak points ASAP. Each roller is designed to have a 10 by 15 by 4 millimeter bearing, which first gets mounted to the roller shaft, then that assembly gets tapped into the outer roller. For a Gen 1 part, it turned out pretty good, but I can definitely foresee the single bearing design having some tipping issues. This is a belt I printed on my P1S using 95A TPU. It's just a test print to see if I got my track pitch correct, which is the spacing between each link. This can be one of the trickiest parts of creating a track-driven system, as getting the final drive teeth and track pitch spacing correct is essential. Having too short or too long of a gap in the track will result in the final drive slipping. I'm happy to say though that on this first print, I think I nailed the spacing, as the final drive teeth seem to be meshing perfectly. So I finished the rest of the track, printed it, enjoyed the sweet, sweet sound of taking it off the build plate, and then proceeded to test out the motion. If you were expecting a track made out of individual links, don't worry, you probably weren't the only one. What I found is that the individual link design has a habit of 1, being a royal pain to assemble, as it usually involves pins for each link, and those pins are usually the weak point as well. This single piece design, where everything gets printed together, is far superior in my opinion, as 95A TPU is extremely durable. By far the most durable material I print with. In fact, if somebody is 3D printing a competitive BattleBot, they're most likely using TPU, as it can just really take a hit and come back. So with the track now done, all I want to do is get it mounted and moving. So I printed out the main body for the dozer, and if you're wondering what this color is, it's Hatchbox Gold PLA. I'm not sponsored by them, I've just been using it for close to 2 years now, as it prints great and feels very construction-y. To mount the final drive to the body, I'm using a 25 by 37 by 7 millimeter bearing. To mount the track, I first place it over the final drive, and then I can pull it over the rollers. It was so immensely satisfying rolling this by hand for the first time, as it glides effortlessly. I also tested its ability to recenter itself if it gets pulled off the rollers, and it passed with flying colors. This is a 12 volt 65 RPM motor I got off of Amazon for $16. A little pricey, but I like the idea of a right angle drive, as it means I won't have to do any weird stacking of the motors inside the body. I will be undervolting this motor at 7.4 volts, but I ran some tests on the power bench and it still seems to provide enough power. An issue I ran into immediately was how to secure the final drive to the output shaft. Due to the location of the bearing and how everything fits together, there's no way to use a grub screw to secure the final drive to the motor shaft, as once it's actually in there, that shaft is covered up by the bearing. I tried coming up with alternative solutions, such as driving in a screw from the side where the threads would bite into the end of the motor shaft, but that didn't really work. Ultimately, I just made the connection super snug and hammered it into place for the time being, which will almost certainly not work and need to be addressed later, but dang it, I want to see this thing move. I soldered on some wires, threw it on the power bench to make sure the final drive wasn't binding up at all. Then came the track, followed by the floor, then my sock-covered foot in a sandal. You are welcome. Generation 2 of the track support involved adding square cutouts, making the roller shafts much easier to mount. And I've also got a cutout for the blade tilt motor wires to go once I get those parts printed. Then of course, there's just more overall detail in this second generation. Because the Dozer now has 2 tracks capable of movement, you better believe I was itching to get this thing moving under radio control, hence the laptop. To start, I just used the semi-truck code as the base, but altered the throttle settings. For comparison, instead of using the bumpers and triggers to control the tracks like I did with the excavator, I'm instead going to use the joysticks, which have the benefit of proportional control, meaning you'll be able to alternate between slow, medium, fast, and anywhere in between as the code registers joystick values between -255 and +255. Also, if you're new here, I always build these projects like robotics projects as I feel it gives you more control on how everything operates. For example, if I'd used standard RC parts, I never would have been able to do the hitching system on the RC Semi, which lets you hands-free hitch to drop decks, side dumps, and cargo trailers, while also sending power and information to them. Because of this robotics twist, I like to use game controllers to control these projects as most people already have them laying around or are familiar with them. I accomplish this by using a code library called BluePad32, which provides a way to call any function a PlayStation controller performs and pair that function with a command. That code then gets uploaded to this ESP32, which if you're familiar with an Arduino microcontroller, it's pretty much the same idea. This little guy specifically costs about $3 to $5, has Wi-Fi and Bluetooth built in, and has pretty good processing speeds. I've used one of these in every project since the skid steer. With everything hooked up and powered, I was so excited I couldn't even wait for the second complete track to finish printing. So I just threw on the skinny test one and started mobbing around my table. Then with the second track finished and a Mo Beta final drive installed, I was able to hit the testing grounds. First stop being the bean pit. My hope for this track design is that anything that gets lodged between the track and roller will be extruded out the side of the track or fall off to the side. Also, by having the final drive up high, it should make it way harder for debris to jam stuff up. I really tried to work it down into these beans, and well, it didn't have a problem with it. I also tried placing beans directly in the track to test this fully, and it had no problem dislodging them, or at least not interfering with the motion of the track. Doing the same thing on the excavator, well, let's just say you're playing a dangerous game. This is a box of car tire weights, and this is a hill. Dozer, climb, hill. The track system still needs a lot of work as the final drive is slipping on the motor shaft, and I don't think the motors really like 7.4 volts. Surprise, surprise. But I'm itching to get the blade put on. Therefore, I'm jumping back into CAD to finish hooking things up. One thing I didn't think about when I first started on this project was how all the angles affect each other. For example, if you tilt the blade, that's going to affect how the lift motors are positioned and vice versa. Doesn't sound like much, but after getting everything hooked up in CAD and moving apart, well, it really didn't like solving those physics. Throwing caution to the wind though, I decided to send stuff off to the printer regardless. The blade is the largest print for this model, and when positioned diagonally on the build plate, it still fits easily. Both left and right lift motors have 3 main pivot points, one here, here, and finally here, which allows for rolling the blade. The tilt motor just mounts directly to the push frame arm, and the wires run down through the inside. This is the only part you really shouldn't print with auto supports, as it'll place supports inside that inner channel, and they are indeed impossible to get out. Also, these wires are meant to be hidden underneath, but I printed the wrong side, so instead they're exposed for now. Before connecting things via remote control, I first took it to a power bench and manually powered each function to make sure it was operating properly. I knew the threaded N20 motors would have more than enough power for the blade applications, but I was still super stoked to see it picking itself up off the table, as well as how hard it pushed against my hand while trying to push it down. I tested blade tilt and blade roll as well. Alright, time for a little self-reflection. Why am I using 7.4 volts? These drive motors are meant for 12 volts, and there would clearly be so much more power to benefit from by using 12 volts. It's really that I wanted this project to be compatible with the semi-truck PCB. But if I want this dozer to be as good as it can possibly be, I'm gonna have to scrap that idea. Enter a 12 volt motor driver. This is an L298N driver and is probably the most simple to use and basic robotics level driver out there. In fact, it's the same motor driver I used to build my robotics project back in school. It's great for quickly testing out 12 volt motors, but it has some major drawbacks, mainly being that it isn't very efficient, hence this massive heat sink. A lot of the power getting sent ends up turning into heat rather than motor movement or dozer pushing power, which is why I'll actually be using these TB6612FNG motor drivers in the long run. They're super similar to the H-bridges I've used in the past, but capable of a higher voltage. Just for testing though, I wired up the old school driver, swapped the 65 RPM motors for 100 RPM motors, and pushed some stuff around. So this is the right angle motor I've been using these last couple weeks. I don't know how I missed this or why it didn't pop into my head, but to achieve this right angle output shaft, this motor uses a worm gear system. That can be great for certain applications, such as where you absolutely don't want whatever it is to be back driven, as the worm gear meshing with the spur gear makes that almost impossible. But given I don't really mind if someone manually moves the track backward, that benefit doesn't really apply to the dozer. In fact, having that worm gear introduces a huge efficiency problem. Worm gear driven gearboxes can be about 40 to 60% efficient, meaning in dozer terms, you could be losing half of your pushing power. Enter a standard spur gear driven gearbox, which has an efficiency rating more along the lines of 80 to 90%. That's a massive difference. I even did some testing on the power bench by attempting to stop the output shaft, and sure enough, even though they were both pulling the same amount of power, the motor with the spur gear driven gearbox was way harder to stop. Because of this, I just spent the last 2 days redesigning the drivetrain on the dozer to use these motors. To make it work, I had to stack them on top of each other, which primarily means the output shafts no longer line up with the final drive. To transfer power from the motor, I now have a simple 2-gear drivetrain, a gear mounted to the motor and a gear that meshes into the final drive. This system was actually a blessing, as the drive shaft slipping issue I had before was easily solved by securing the gear on the motor shaft using 2 grub screws, as that bearing was no longer in the way. And then the output gear has this big square extrusion which fits into the final drive and is locked together with a screw. There will be no slipping here. Fitting the motor assembly into the body did require yet another reprint, and it was such a tight fit I actually had to carve out a channel in the side for the motor shaft to slide down into. Don't worry, this will be plugged so debris can't make its way in. How the motor assembly just slides down into place is super satisfying. Then the whole thing can be easily secured using 2 screws on the bottom. Testing the assembly on the power bench, things are already running smoother. There's now a consistent running sound versus the old right angle motors which had this on and off whirring sound. Transferring the blade components over was straightforward, as again it's kind of its own assembly, so I just detached the lift and push frame mounting points, then remounted the whole thing on the new body. One of the biggest headaches of this entire build was when I went to mount the right side track and realized the motor shaft was smack dab in the middle of the track path. On the left side, this isn't an issue as the motor is mounted lower, so that was at least a relief. I bounced around in CAD for a couple hours trying to come up with ways of fixing this without winding the entire model. The solution hit me when I realized that I could just increase the module of the right side gears, which is basically just increasing the size of the teeth, therefore pushing the motor further out and allowing me to slide it back past the left side gears. The gear ratio stays the same, meaning one track isn't going to now be way faster than the other, just the gears themselves are a little bigger now. I did have to get a little destructive on the old dozer body to make this new module fit, but hey, what's having to print just one more iteration? Running it on the power bench, this thing is going to absolutely rip. Between switching from 7.4 volts to 12 volts, as well as more efficient motors, this thing has gobs and gobs of power, though it's lacking in one crucial aspect: electrical tidiness. Therefore, I started working on the dozer PCB. It'll be placed flat up against the front of the dozer, and because that's a relatively large space to work with, I was able to place all the components on one side of the circuit board, which makes soldering a whole lot easier. Because it'll take a couple days for these to arrive, I'll need something else to keep my hands busy, aka the top assembly. I spent a significant amount of time on this section, the main goals being that I want it to 1, look good, of course, 2, seal up the top of the body so nothing can get in, and 3, be durable. Skipping the nitty gritty, I just printed it out. The interior might be my favorite part as it's got little joystick and throttle controls, as well as lots of buttons and screens. It also just pops directly into the cab, and who doesn't like a built-in clip system? The engine cover mounts to the cab via one screw, cab gets mounted to the upper body, then the lower body, and the result, in my opinion, is pretty flippin' sweet. Plus, after tucking all the wires and making one quick haphazard modification, the top fits on relatively well. There are 2 front indents in the motor cover that latch onto these extrusions in the body. It then seals around the top edge and will eventually be secured via a twist knob in the back. And now that that is all done, my PCBs have arrived, and I wasted no time in getting everything soldered on and reprogrammed to match the new outputs I set, which is when I hit a roadblock. I completely forgot to enable motor outputs on the PCB by applying power to both PWM pins, which by default are pulled low. I know they say PWM, which should mean I'm sending variable pulses to control each motor speed, but I'm already doing that via N1 and N2. Because of this, no matter what I did code-wise, nothing worked. It wasn't until I soldered on this sketchy jumper wire that things started to move. I was able to correct this connection on the PCB in about 5 minutes and get them reordered, but it would be another couple of days before I got them. Actually, I need to touch on one more electrical thing. Providing the 12 volts are 3 Phoenix 18650 batteries, which are absolutely phenomenal as they have overcharge and discharge protection built in, as well as a built-in micro USB charger. Before I start my whole spiel here, I just want to say again that I am not sponsored by Phoenix. I've never spoken to them, but if you don't know, they build super high-powered flashlights and headlamps. To power those devices, they make these high-quality batteries, and they are some of the best on the market because of the features previously described. But more importantly, for my RC construction equipment, is that they can output a lot of current in comparison to other rechargeable batteries of this variety. For example, the excavator runs off of 2 16340 Phoenix batteries, which can output more than 2 amps. This is great because when you're moving a big stick around, you might be pulling upwards of 1.5 amps. Now here's some generic rechargeable ones off Amazon. I don't care what their claimed specs are down below, half of them shut down after outputting more than half of an amp. That's why I recommend these Phoenix batteries. To get these into the dozer, I first started with a flat 3D printed battery tray, which did not work out, especially when trying to fit the top cover on, so I 3D printed this triangle design, inserted some metal clips, and soldered the connections with a flow path as shown. This can then just be slotted down into the dozer body. Okay, now we can move on. Up first on my list of demonstrations is a get the heck out of the way test, which features a log truck, haul truck, side dump, and for extra credit, a power supply. For run 1, I've added no additional weight to the dozer. Now I'm going to give the dozer some extra weight via this box of 1/4 ounce car tire weights. Next, I took a spin around my table and tried pushing some sticks, tested out the climbing capabilities, and eventually, of course, climbed the mountain. Finally, if you had any doubts whatsoever, I pulled my Form 4 around in a wagon, which was a good initial test to see if it'll be able to pull me in a wagon. After all of that, the motors were warm, but definitely not hot, which is a great sign. These square edges are an absolute menace when it comes to turning on carpet, as they get caught and make the dozer jump all around. To fix this, I simply chamfered the edges a little, so they should slide sideways easier. Side by side, you can get a better visualization of the difference, and then moving them by hand on the carpet, you can first see the square edge track, which gets caught, versus the chamfered edge track, which slides much smoother. Same story when it's on the dozer as well. At this point, I've done about all I can with this old version of the dozer body, as things like the ripper and top shell lock were made to work with a newer version. So I printed out yet another body and got to work transferring everything over. The top lock on this version works much better than I could have hoped, as the top edge of the body seals around the indent in the top shell and snaps down with a satisfying click. The ripper went on almost without issue. The blade, which was printed with silver silk PLA+, gets mounted inside the ripper body using one screw. Then the lower and upper control arms get mounted to that with their respective motor/servo. The result, when powered, is a ripper that can tilt as well as lift the whole body off of the ground. Only a couple more things and the dozer will be ready for its first real world test. And because I'm excited to show those clips, I'm just gonna go ahead and speed run these last changes. Printed out the rear guardrail for the top assembly, which gives the model a more balanced look, added an exhaust and air intake section for the engine cover, modified a bunch of parts to allow me to add these car tire weights in. For example, this track support weighs 2.2 ounces off the printer, but after adding some weight, it now weighs 8.2 ounces. I didn't end up getting an accurate reading on the dozer before I put weight in, but if I had to ballpark, I added around 25 to 30 ounces, or almost 2 pounds of additional weight. Before hitting the sand, these are the remaining pieces that need to be added. One, this motor slot cover, which covers up the motor shaft slot and just snaps into place. Two, this is a motor place holder to balance out the tilt motor on the other side. Three, the grill, which also snaps into place and looks. 4, these little guardrails on each side, and 5, finally the final iteration of the roller. It is now officially beach time.
In a world where an RC dozer immediately breaks.
Yeah, so after getting to the beach, I broke the dozer right where the lift motor connects to the body, which seriously limited what I was able to do. Nevertheless, I still made the best of it because it was a 2-hour drive to get there. Even with one lift motor out of action, I was still able to push some sand around, but the true star of the show was the Ripper. While building this, I thought there was no way the Ripper would actually be functional on a lightweight RC dozer, but I was completely wrong. This Ripper works great for loosening up tough clumps of sand or dirt, and then coming at it with the blade. Not only that, but you can also use it to climb up ledges. Overall, this first beach test was tremendous in pointing out what needed to be reworked. Addressing these issues took very little time, and after a day of printing, I had another iteration. This time with beefed up motor mounts, slightly better rollers, and just for fun, some new TPU tracks printed in the same color gold as the body. Instead of the beach, I opted for the dirt pile in my backyard as it's not a 2-hour drive. The downside though is this stuff is way harder to break up than sand. Nevertheless, I made it my mission to cut a road to the top, and man do I have so much more respect for dozer operators, as it's one thing to just push a pile of material, it's a whole other thing to be thinking ahead and maneuvering material into place so that you end up where you want. For instance, it took me an entire hour to make it to the top of this 2-foot hill. The only issue I had was the left track would occasionally get clogged with soil, especially when sideways on a slope, causing it to derail. Luckily, you can just shake the dirt out and remount the track without doing any work. Overall, I was really pleased with how it held up, meaning it's time to try that beach day again.
In a world where an RC dozer gets to work.
Also, you are able to load the dozer onto the drop deck trailer. I just completely forgot to bring the RC semi to the beach. So I hope these couple clips here make up for it. Now, if you want to 3D print and build your own RC dozer, you can by joining the Professor Boots workshop on my website, professorboots.com. There I have step-by-step guides that take you through how to 3D print the parts, source components, coding, assembly, etc. Once you join the workshop, you'll have access to all 9 builds, as well as weekly update videos under the build log section. For example, workshop members have actually known and been following along with the dozer since August. The workshop is the primary way this channel is supported, and how I get time to actually build, test, and make these videos. So a huge thank you to everyone who's a member. So it's time to choose the next project. As always, whatever piece of machinery gets the most comments down below will be the next project. So let me know what piece of equipment you'd like to see added to the fleet next. With that, thank you all so much for watching, and I'll see you here soon with another build.